Okay, good morning for everybody. Again, welcome here to the Academic Arab College for Education. I hope for you a very interesting and benefit day. I just want to say some few words before I start my presentation. That today I'm very excited because this is my first lecture after the birth of my son, after I'm getting a mother for the first time. So I present I present for my son Fabi, and I want to say to him that I love him very much. I want to talk today about...
כדאי להחשיך קצת את האור.
Okay, I want to talk today about a lab activity which was held here in the college. It's a collaboration work between me and Dr. Bashir, Dr. Ahmad Bashir, and Dr. Muhammad Hujirat. This lab activity was published recently in the Journal of Chemical Education, and it's called Going Inside Colored Solutions, the Optical Microscope as a Tool for Studying the Chemistry of Hydrophilic and Hydrophobic Materials. I think that all of you agree that the most common question among students concerning polar, apolar liquids, hydrophilic and hydrophobic materials is why oil and water don't mix. I think that you agree for me. And I prefer always when we want to teach about hydrophilic and hydrophobic materials to start with the simple and the familiar experiment of magic sand. We can let the students try hardly to wet the sand and they will never succeed. So the student will ask, how can something submerge in water and stay dry? And students, we can conclude that some things just don't get along well with each other. For example, we can take oil and water, we can hardly try to mix them, and they will never become friends. And in other words, they will never be mixed. Maybe we can do this. Theoretically, in order to explain to students this phenomena, we have to explain what does that mean hydrophobic material, its chemical structure, its chemical nature, and also what does that mean hydrophilic material, also its chemical structure. We can take the water molecule as an example for a polar molecule, hydrophilic molecule, and we can take also an example of oil molecule as an example of hydrophobic material. And then the students can conclude why this chemically why these materials can't be dissolved in each other. But we have to say that it's not a big problem that some materials can't be mixed, because we need it in our everyday life in some cases. For example, imagine what would happen to a cell if its membrane dissolved in water. Okay, I think it will interest the students here. And despite the fact that oil and water can be mixed, scientists succeeded to do this by using surfactant materials, surface active agents. These are materials which has a very unique structure called amphiphilic structures. It has two parts, or these materials combine two features in its chemical structure. A part, the hydrophobic part, which is usually composed of long hydrophobic hydrocarbon tails and a polar head group. These surfactants or these materials could help to mix oil and water, and this is the reason why we use in our everyday life detergents and salt for cleaning oil and organic soil, because water can't do this, and these detergents are some kind of surfactants. Here are some examples of detergents which are used at home in everyday life, and we can see the hydrophobic part and the hydrophilic part of it. And when we mix oil, water, or any hydrophilic and hydrophobic liquids with a surfactant, we can get a solution which is called an emulsion. Okay. What's that mean, emulsion? We have to say that surfactant is a molecule which has two sides, one hydrophobic and one hydrophilic. and it has to organize itself by the way that its hydrophobic side or its hydrophobic part will orient towards the oil molecules or hydrophobic materials, and on the other hand, the hydrophilic part of it will be oriented to water or any hydrophilic material. This is producing very unique structures which called micelles, and that this is the way how this surfactant could mix water and oil and any other materials, hydrophobic and hydrophilic materials. So there are different or several publications in literature which concerning these concepts and a different point of view. But here we present a lab activity which is consists of two parts. Firstly, I want to talk about the first part of it. This lab activity let the students explore these concepts: hydrophilic, hydrophobic, emulsions, surfactants, detergents, and so on, by a new twist. And the students could explore the solution mode of different hydrophobic and hydrophilic materials in different environments. So for this purpose, we have prepared a series of red-colored solutions which are seemingly look the same, but by viewing inside these solutions using an optical microscope, we could explore by a different way the hydrophobic and hydrophilic nature of different substances. So we have different red-colored solutions viewing by microscope, and this let the students explore the unique different structures which they will reveal by the microscope. What are the components of the solutions? We use double distilled water for the water space, vegetable oil, phosphatidylcholine. This is the structure of phosphatidylcholine act as a surfactant. It is very important to manage that it has two hydrocarbon tails in its hydrophobic part, and we use a hydrophilic red color and also a hydrophobic red color. This is the hydrophilic red color, and this is the structure of the hydrophobic red color. Okay, what was the student role? We have two groups for this lab activity. 20 upper-level high school students majoring in biotechnology and 21st year college students majoring in chemistry perform the laboratory in separate occasions, and the students prepare the solutions and viewed it on the optical microscope by themselves. Okay, so we have 8 solutions. 6 of these solutions are red colored solutions, okay? And but when they view these solutions by a microscope, the students reveal different structures. Okay. What are the first 2 solutions we prepared? In the first step, we choose to prepare just aqueous solution of the surfactant, aqueous solution of phosphatidylcholine. In the first one, we add hydrophilic red color, and in the second one, we add hydrophobic red color. The students prepare these 2 solutions, and they get 2 red colored solutions which are seemingly look the same. They are red colored solutions. But when they view these solutions by the optical microscope, they reveal different structures. In the case of hydrophilic red color, they get a colored background with a transparent circle structures. In contrast, when they use the hydrophobic red color, they get a transparent background, lined circle structures which are also transparent in the interior part of it. So the question is why we get different structures. It is related to the dissolution mode of the surfactant on water. We know that this molecule has 2 tails, 2 hydrocarbon tails, which are hydrophobic. So when we want to dissolve this material into water, the hydrophobic tails has to be far away from the water molecules. The surfactant do this by introducing a bilayer structure which is called liposome, we can see here that the interior part of the liposome are the hydrophobic part of it, and they will be far away from the water molecules. They will not be in contact with the water molecules. So, based on these structures, when we add hydrophilic red color, it will be spread on the all the solution, and it will not be go inside the cycles, because the hydrophobic part of this liposome structure acts as a barrier against this the red color to go in the interior side of the circles. But when we add the hydrophobic red color, we can see that we have aligned circle structures, because the hydrophobic red colors go just to the site where the hydrophobic part of the surfactant. In the continuous of this experiment, we firstly prepared 3 solutions of oil in water emulsions. That means a dispersion of oil spots into a medium of water. And in the first one, we didn't add any dye. In the second one, we add hydrophilic red color, and then we add hydrophobic red color. We get 3 solutions. 2 of it are red colored solutions because of the dye that we add. But when viewing by the optical microscope, we see that there are a difference in the structure or the interior structure of these 3 solutions. In the case of the solution without the dye, we get spherical structures which are transparent, and also the background is transparent. But when we add the hydrophilic red color, you can see here that we had a transparent circle structures and a colored background. In contrast with the hydrophobic red color, we have colored spherical structures and transparent background. And this is just because the micelles which are introduced in the solution by the phosphatidylcholine. Phosphatidylcholine could mix the water and the oil, could disperse the oil droplets into water by producing the micelle structures in that way that the oil droplets here is the oil droplets which are surrounded by the surfactant from the hydrophobic part of it. So the question is, what will happen if we now prepare water in oil emulsion? We disperse droplets of water into a medium of oil. We think that we have to get the same pictures or the same image, but in contrast. And we, for this purpose, will prepare more 3 solutions. And these are the results. You can see that for hydrophilic red color, we get here a colored spherical structures in contrast of when we use the oil in water emulsions. We just get the same pictures but in contrast. Okay. Another part of this lab activity is just we take a switch in this step of this activity, and they ask themselves if we could reduce the size of these structures from microscale to nanometer scale. Could we get anything here? The answer is yes, because if we succeed to reduce the size of the spherical structures from micro to nanometer scales, we getting now the field of nano science. Why it is important? Because nanotechnology. What does that mean? Nanotechnology. Nanotechnology is the developments on the nanometer scale. Usually we talk about from 1 nanometer to 1000 nanometer. This is the science of all the materials in the nanometer scale. And what about emulsion? In emulsions, we also had microemulsion with spherical structures or micelles in any structure in the micro scale. And when we reduce the size of these structures to in nanometers, we talk about 0.1 to 0.5 micrometer. Micrometer is about 500 nanometer, as we get different results. First of all, can we do this by a simple way? The answer is yes, because by this simple apparatus, which is very simple to use and also it's very cheap, we have just to move the solution across a membrane, which is on it, several times, and we get a nano emulsion. Okay? So in the first step, we could do this. And why it is important for the students? Because we want to let the students test slightly what that means nanotechnology, what that means nanomaterials, what is important, okay? And we have to say, let me just to say a few words before I continue talking about the nanoemulsions, that this is important because the properties of a material change dramatically. We can't change dramatically when we convert it from the bulk scale to a nanometer scale. For example, take this picture. This picture is colored, different colored here, yeah? I want to say that all the colors here are made of from just one sample, gold nanoparticles, which has a different size. Each size of particle gives a different color. Okay? And I want just to talk about another example which is interesting, that for a sheet of aluminum foil is handy way to keep your sandwiches. Yeah, and we use it at home, in kitchen, and inside the oven, and so over. Okay, but if you take that same aluminum sheet and grind it into smaller and smaller pieces, when they became very, very tiny in the nano size scale, something odd happens. They start to explode. The same material, just cut it to particles with a nanometer size. This makes aluminum nanoparticles great for putting in rocket fuels, okay? But probably not something you want near with your lunch. And what about our nanoemulsion? When we convert our microemulsion to the nanoemulsion, first of all, the solution start to become more transparent, okay? And the students could realize also that these solutions are more stable against the gravitational energy because of its Brownian motion, okay? And also, we can use the Tyndall effect for introducing the students about the difference between micro and nanometer scale. What does that mean, Tyndall effect? I just want to say that if we compare between true solution like sugar or salt in water and a solution of particles with a nanometer size, and we want to use a beam of laser to move a beam of laser through this solution, we can see that for a true solution, the beam moves without anything. We can't see anything. But in the solution which contains a nanometer particles, you can see here, I don't know if you could see a very shiny line. You can see a red shiny line. Why this happened? Because of the scattering of the light when it gets to the nanoparticles inside the solution. Okay? So, what will happen in our solutions when we move from micro to nanometer size micelles. I think, and you surely think that the Tyndall effect will be minimized dramatically. Why? Because in the microemulsion we have a micro-sized spherical structure, and we convert it to a nanometer structures, so the beam can across this solution more easily. Okay, so the question, if we succeed to this toward the students, the answer is yes. First of all, we take just the first two solutions, which are aqueous solutions of phosphatidylcholine, and we use a membrane of 400 nanometers, not less, and we have reduced the size of the micelle structures. You can see here, and you can see that this is an example of a solution. This is the micro emulsion solution. You can see here the shiny spots inside the solution. This is because of the scattering of the light by the micro-sized spherical structures. And when we minimize that or reduce the size of the spherical structures to nanometer size, the same solution became more transparent. You can see here, and it's more difficult. It's difficult to see the shiny spots. It still exists because we have 400 nanometer size spherical structures, but it will be less. That's it. Thank you for your attention.
Any questions for Riyad?
الناس بالعربي كل اللي انت عرضتيه عنده شيء بالكيمياء، كل شيء انت عرضتي لنا اياه هون يعني هو كتجربه اللي ممكن تكون طريقه تعليم جيده للطلاب. ما قدرتش اصل بمفهومي الشخصي للاسقاطات، يعني هذا الموضوع وهذا المشروع يعني اللي انتم عرضتوه هون اليوم، انه لوين بيودي اجتماعيا، اقتصاديا، فكريا. يعني انا ما قدرتش افهم غير انه التجربه حلوه وفرجتني اشياء حلوه، ما قدرتش افهم لوين بودي.
هدفنا كان في هاي التجربه.
אולי תתרגם לעברית או לאנגלית?
اوكي.
כולם אומרים. ריאן, קודם תגידי בעברית, אחר כך תגידי באנגלית, ואחר כך תגידי בערבית. הוא יתרגם לערבית מדוברת.
אולי אנחנו צריכים ללמוד באמת, הוא שאל לאן זה מוביל. He asked that what's where would lead to this lab activity. I want to say that in this lab activity you can teach everything in science theoretically, yeah? Okay. But it's very boring, and it will not be. It's not a good way to teach science just by theory. Okay? So there are basic concepts in chemistry. Hydrophilic, hydrophobic materials, and we can see a lot of phenomena in our everyday life concerning these concepts. Okay? We here present lab activity, an experiment, very simple experiment, which could help the students understand these materials, the chemical structure, the chemical nature, and how these materials behave in different environments, okay? And this also could explain a lot of phenomena in our everyday life. For example, why do you use a soap for cleaning? You can clean yourself just by water. The answer is not. And we can take an example of, as I said, the cell membrane, and a lot of things in our village. I hope that I answered your question.
You can use also this in painting. If you the different size of the particle in different colors, you can use in painting.
Of
If
course.
you want something
Art.
relevant in art.
Art. I want to say just few words also that we want also to publish
Second art.
a second article on nanomaterials, and I hope it will be interesting for you and you can see a lot of things.
May I say just very quickly that the United States several years ago gave a very dramatic demonstration of emulsions when we had the Deepwater Horizon oil spill in the Gulf of Mexico, and they pumped thousands of tons probably of surfactants into the leaking oil. Now underneath the Gulf of Mexico, it's not nanoscale. It's a global scale emulsion of oil and surfactants underneath the ocean. So perhaps that will connect also.
And how do you wash it by soap?
بس بالعربي لا حياتنا بمكسيكو
לא שומעים.
اسألي بالعربي اسألي بالعربي حبيبتي.
احنا دايما بنعلم الطلاب انه وانتم يعني احنا كمان تعلمنا واحنا صغار المي والزيت نيفر ميكس. اسا بينفع نقولن انه بلا بظبط انه
يعني next, but we have to add another material. And I prefer that you can take soap as an example. Why soap? Because we use it in everyday life. Why we use soap and shampoo and other detergents for cleaning? Just because the water can't clean or can't mix with these oily things. So we use these materials.
I think every housewife should know something about chemistry and materialistic interactions. So her presentation is very important and connected to our daily life. It's not separate from our daily life. My wife, your wife should know something about chemistry and how materials interact in daily life. She prepares food, this is chemistry. We drink, this is chemistry. We go to the bathroom even, it is chemistry. So chemistry is an integral part of our life, and everyone should know chemistry before he gets married.
So can he?
Yes.